Welcome to Study Loop.
So when the given ball bounces and the ball is filled with nitrogen gas, we can model this as a adiabatic process. This is a very sudden and very quick compression, and it is certainly going to be an adiabatic compression. So the volume of the ball changes due to bouncing, goes from this initial volume V1 to the final volume V2, and we're also given the diameter of the ball, which is here converted into meters, from centimeters to meters. So for the part A of this problem, we need to evaluate the maximum temperature T2, and this is the temperature after the compression. So we know that when there is an adiabatic compression, the temperature will change due to change of the volume. And we can use the textbook formula that says that T1 times V1 on gamma minus 1 is going to be equal to T2 V2 gamma minus 1. Therefore, this final T2 is going to be Tmax. This is going to be the maximum temperature that gas can reach after compression. Since we are modeling this compression as adiabatic, every other kind of compression will go to the lesser temperature. So this is the maximum temperature that it can reach due to sudden compression. So we can say that T2 equals T1 and then the ratio V1 over V2 gamma minus 1. So we can then substitute that T2 equals T1 V1 over 0.8. We know this is 80% of change between V1 and V2 gamma minus 1. Substituting the actual values, we see that this 293 kelvins, and this is going to be 1 over 0.8 on 0.4, since this is 1.4 minus 1. And finally, we obtain that T2 equals 320 kelvins, which is converted into Celsius, and this is equal to 47 degrees Celsius. So this is how much it becomes hotter inside the ball due to bouncing. If we consider bouncing as an adiabatic process, and it is an adiabatic process, it is happening very suddenly. So for the part B of this problem, we need to find the change in internal energy, and this is going to be a little bit more complicated. First, we need to find the volume. We need to exactly know the initial volume of the ball. So this volume will be V1 equals, from the geometry, we know that this volume of a sphere is 4 over 3 times p times radius to the third power. Since we're given the diameter, we know that radius equals diameter half. So V1 then equals 4, 3 pi, and then this diameter on half on the third power. Substituting the known values, we see that this 4 over 3 times pi times, and here we can immediately say that this is 11.95 times 10 to the minus 2 meters, and this is on the third power. So when we evaluate this, it becomes 7.15 times 10 to the minus third meters cubed. And this is an important value. We will use it in the problem. So next, we need to express the change. And we will again approximate that the change in volume is enoughly small that we can use the heat capacity for the constant volume. This is CV. So the total change of internal energy can be said to be molars, number of moles, times CV, and the change in temperature, which we know we already calculated it, the T2. So from here, we now need to actually find the number of moles. This can be also done from the ideal gas law. We know that PV equals nRT, and from here N equals, this is going to be all for initial conditions, so P1 V1 over R T1. And this is exactly what we can use to evaluate the number of moles. So separately from, we will return back to this equation. We will now just evaluate N equals, and we will substitute the known values. It's going to be a big rational expression. So 2 times 1.013 times 10 to the 5th power Pascal, this is pressure, times now what we already calculated, the volume, minus 3, times meters cubed, and then 8.314 joules per mole Kelvin, times 293 kelvins. This is equal to 0.594 moles. Now we can finally go back to the equation of internal energy change. So delta U equals, we will now immediately substitute all of the evaluated quantities. So this is going to be 0.594 moles times 20.76 joules per mole Kelvin, and then times the change in temperature, which is 320 minus 293. I'll just write this down better. 93, and this is in kelvins. Placing these values into a calculator, we evaluate that the change in internal energy is equal to 333 joules. And we see that the change is positive. So this is certainly an adiabatic compression. Now the problem is solved completely, and I hope you find this helpful, and I hope to see you in another lesson.